This is 141, and tonight it is hashing. So we'll talk about hash functions, and then I'll do I'll demonstrate the first RSA project. But codebook, yeah, I'm not quite sure what that's all about, that codebook stuff. And here's port Swigger status. Let's take a look at that. Yeah, that's right. Thanks. I forgot to mention that. I'm glad you posted it. You can get your burp certification free if you do it this year, apparently. Yeah, good. Otherwise, it's 99 bucks. All right, so let's talk about hash functions. Oh, and I ought to get my camera working. I've got to adjust the properties. There we go. All right. So we'll talk about secure hash functions, how they're built, the SHA family, which is the main one, and Blake, a new one. All right. So hash functions are used almost everywhere. No, I don't. Well, I mean, if you talk about the burp certification, you need to learn how to use burp, and there's no real prerequisites for that. But it's a whole course worth of work. Absolutely. I don't think you need to know much in the first place, except it would be nice to know a little bit about web protocols. But it's a lot of work. I would say students who take my 129S would probably be like 2/3 of the way there. Yeah, you have to go through the Port Swigger Academy. That's the point. Yeah. Yeah. Twisted Nose, he took that course and went through the Port Swigger Academy. That's what it's for. Yeah. All right. So you got in digital signatures, you have something like a public document, like a deed, and then you want to sign it. So you hash it and then sign the hash is how you typically do it. Public key encryption uses hash values to authenticate the keys and such. And, oh, I thought you took it wrong. Anyway, so, and then the primary one is verification of messages or files. You put a hash value on it, and that acts like a fingerprint. So if you make a copy of that document, you can recalculate the hash and make sure that it's an exact copy, that nothing has been altered. And many rounds of hash functions are used to hash passwords these days with bcrypt or scrypt, so that it's very difficult to take the hashed password and recover the original plaintext password from it. So, last point, the main point of a hash function, it creates a fingerprint. You can have an input of any size, like a whole big file, and you can hash it and you get a fixed length hash. It is not encryption because it destroys information. If you have 1,000 bits coming in and only 160 bits coming out, you have obviously destroyed information. There is no possible going back. It can't be reversed. There is no key. It is a way to create a fingerprint of a file. It is not an encrypted version of a file. There's one thing I see people do sometimes. Sometimes people want to post a record that they knew something without announcing the secret. So I've seen people that put like hashes in Twitter. And you can't reverse them, so you don't know what they're saying. But then when something happens like next month, they can say, I knew that first. And that's a way to prove that you know something at a certain time. Yeah. Yep. Anyway. So there are hash functions that are not cryptographically secure, that can be easily faked. For example, CRC32 is a 32-bit hash. It is far too short to have any real security. The point of it is not to do something like hash a password and resist an intelligent attacker. The point is to detect bits that are dropped when transmitting through Ethernet cables or Wi-Fi. So if you send a packet, it sends it along with a frame at layer 2. At the other end, the NIC will compare that to the CRC32, and if it doesn't match, it'll say, this is a damaged frame, please resend. And it's very easy. You could maliciously modify a frame and maliciously change the CRC32 to match, or even modify it in a way that would keep the CRC32 the same and get away with it. But it will detect accidental errors due to electronic defects in the transmission system. But secure hash functions are intended to make fingerprints that are so trustworthy that even an intelligent attacker using a powerful computer is not able to fool them. So, for digital signature, you have a message of some kind, you calculate the hash, then you use a signing key and you sign it, and now you have a digital signature here, and the digital signature is actually of the hash, and you can verify it by taking the message, which is not a secret, and recalculating the hash, And of course, if you were able to make a second message that had the same hash, you could fool this system, so it relies upon the fact that the hash is a unique fingerprint from the message. Good? So hashes should be unpredictable, like all other forms of encryption. We talked about this. This is the issues of diffusion and dispersion. So if you change just one bit, like go from A to B to C, everything about the hash changes. This is a good property. That's why this is SHA-256 in the SHA-2 family, and that's a good strong hash. Good strong hashes have this property. You change even one bit of the input, everything in the output changes. All right. But all hash functions are non-unique. If you have 1,000 bits coming in and a hash 256 bits long, there are 2 to the 1024 possible inputs, but only 2 to the 256 possible outputs. So there are many messages that hash to the same value. In principle, there are always hash collisions. That's what that's called. So it is absolutely not true, in principle, that there is only one message that would create that hash. In fact, there are many more messages that would create the same hash. But what you want is for it to be impossible to find them in practice. So you want them to be so widely spaced out that even if you took all the computers in the world and all the time in the world, you'd never be able to find another message that had the same hash. And then in practice, the hash is one way, and in practice unique. And also, there's the issue mentioned here. I'm describing a different one there as pre-image resistance, actually. This is one-wayness, which means that you cannot take the hash and deduce the message from it. In principle, that's of course always true because there are many messages attached to the same value, but you want it to also be true in practice. This is pre-image resistance. That's what I was saying. If you know a hash, you cannot find any message at that hash, even if you'll settle for any message, not necessarily the right message, which is essentially the same thing as the previous one. This means I have the image, but I can't find the pre-image, the thing before it. I have the hash, but I can't find the message that led to the hash. And that's, of course, what you want for passwords. You want to have hash passwords on the system, and if somebody steals that file, like just happened to Twitch, apparently, you want them not to be able to deduce the passwords from those hashes. So if you want to see how hard would it be to calculate a pre-image, the naive, in fact, this is the only good way, I think, unless there's a mathematical flaw in the system. If you have 256-bit hashes, you're going to have to do 2 to the 256 calculations. You're going to have to calculate 2 to the 256 hashes to find any particular value in principle. So that would be forever. As we said, even 2 to the 100 is more calculations than you can ever do. So anything above 100 is very secure. And you're not going to have the problem unless there's some kind of mathematical flaw in your hash function that makes it possible to take a shortcut. And the second pre-image means you have a message and its hash, and you're trying to find another message that goes to the same hash. And that's essentially the same as the first pre-image resistance, unless you have a mathematical defect, and there is a common mathematical defect in most of the hash functions that we use, called length extension, that makes this possible, and that's why this is the type of collision that Google found in SHA-1. This type of collision can be found much more easily than the others for hash functions of the type that we are currently using. So, every hash function has collisions, and the reason why if you calculate 2 to the 256 possible hashes, and there's only 2 to the 256 possible results, then you begin to have the pigeonhole principle. You know, at some point you're going to see a collision. All right, but what you're hoping is that you cannot find any of those collisions because they're very far apart. So to see how far apart they are, you consider the birthday attack. If you have students in a classroom and you go around and ask for your day and month of birthday, then there's only 365 possible days. And so if you have 23 people, the first person picks a birthday, and that's fine. The second person, in order to make sure they don't duplicate this birthday, there's only 364 possible birthdays that will not create a collision. Okay, now there's 2 known values. The next one only has 363 days that will not create a collision. The next one has 362, and so on. This is the probability of all the birthdays being different. And it turns out, by the 23rd term, this has fallen below 50%. So you have a more than 50% chance of having a collision when there's only 23 people in the classroom. And in fact, the general principle is, if you have a 2 to the n hash values, you only need to go to the square root of that number before you'll find a collision. because if you calculate 2 to the n over 2 hashes, then you have 2 to the n over 2 squared pairs to compare. And so that is more than 50% chance generally that you'll find a collision. And that's the point of the Rho, Pollard's Rho that you've already played with in the project, which we'll talk about a little later. Anyway, so here's the naive birthday attack. You compute 2 to the n hashes of 2 to the n over 2 hashes of 2 to the n over 2 arbitrary messages. Then you sort them and try to find consecutive entries. And so this is the simple birthday attack. Take 2 to the n over 2 calculations, 2 to the n over 2 units of storage, which is what we were doing. We were doing this project last time. You have to store all the hashes and hunt through the list every time you have a new one to see if you've got if you found a collision. And so there's approximately 2 to the n over 2 calculations, but you might take a few steps for each one of those. Anyway, I added some stuff that's not in the book because I was interested in how secure things are, so I decided to look for an MD5. So here's the pre-image attack. MD5 is 128 bits long. And so how can you find a hash with MD5? You calculate every possible hash would be 2 to the 128. So if you wanted to find a particular hash value, you could never do that. 2 to the 128 is undoable. But that's impossible if you said that 100 is enough. And here's the experimental test of how many bits it takes to be secure. The best one is the RSA Security. Made some challenges. And a 56-bit key has been cracked by brute force and a 64-bit key by brute force. But I don't know. Oh, the green. The green affects it because I'm using a green screen. Anyway, the 72-bit key is going to take another 100 years to crack. So no one has ever cracked a 72-bit key by brute force. So that's why we say 100 bits is probably enough. Although, there's another way to look at it, which is Bitcoin. Bitcoin is, as you know, a huge network of computers, people making the biggest, fastest computers in the world, and the total Bitcoin mining is now up to 2 to the 93 hashes per year. So if people were as motivated as all the Bitcoin miners in the world, they could crack a 93-bit hash, a 93-bit key by brute force in a year, apparently. So maybe we should be readjusting our consideration, and there's where you have to do threat modeling. I mean, how much does somebody want your password? Probably not enough to spend more than a day of computing on one machine for it. But if you're trying to hack, say, the United States election and alter the presidents, then they probably are motivated enough to actually mobilize these monstrous resources like our enemy nations. Somebody there? I'm hearing some knocking around. Okay, anyway. So that's why this is a common issue. Some people think we should have internet voting, like unfortunately Andrew Yang thinks that. And all the security experts have said absolutely not, because the election in the United States is so important that people will devote monstrous resources to attacking it. And they're knocking on the floor upstairs. And therefore, our security procedures on the internet are not remotely strong enough for that. Anyway, so that's a test of... So if you want to consider if the maximum computing available to any attacker is 2 to the 96 and pre-image takes 2 to the 128 calculations, then you got 2 to the 30 between those two approximately, and that's a huge amount. So for the pre-image attack, where you try to find the message that will hash to a specific value, MD5 is essentially unbreakable. But for the naive birthday attack, you only need to get to 2 to the 64, which is the square root of 2 to the 128, and that is easy to do. As we said, you certainly have enough time to do that. And that's why there's software you can run that will create MD5 collisions. But the 2 to the 64 calculations is not impossible. But what if you wanted to store 2 to the 64 bytes of RAM? Well, that turns out to be 16 exabytes, which is kind of a lot. 16 million terabytes, kind of a lot to buy, but actually not impossible on global scale. That's only about 1% of the Earth's total storage. So once again, if you really wanted to do it, and you were a powerful nation, like if the US NSA really wanted to do it, they probably could do it. And there's the storage capacity going up to about 2,500 exabytes. Anyway, so, but if you wanted to do the pre-image attack storing them all, you could have to store 2 to the 128 units, and you'd never be able to do that. Anyway, so here's the Rho method. You could just calculate hashes of numbers, 1, 2, 3, 4, looking for a collision, but it turns out that this is a much better way to do it, Pollard's Rho, which is what we did in the projects. You start with a starting value and hash it, then you hash that, and so on. And this means that you calculate your hash 1, 2, 3, 4, 5, and eventually you'll get a collision where the new hash value repeats one of the others, and from then on you'll just go around this loop forever because you did it this way. If you just hashed counting numbers, you wouldn't have this loop pattern. And the fact and the length of this, you know that the time it takes to find the first collision is approximately the square root of the number of possible hashes. So you know how long it will take to reach this point. So that means the tail and the circle are both approximately 2 to the n over 2 long. And since you know it's going to be going in a whole loop, you don't need to store all the hash values because that might be too much to store. So what you do is you pick only certain hashes to store, like ones that start with 3 zeros or something. So the storage is cut down greatly. And even though you don't store them all, you know that you'll eventually find the collision because one of the ones on this loop will have that property, and you'll eventually hit that number again. So you might have to go further. What will happen is if you're calculating, and it is this one down here that is the distinguished value, then you'll have to keep going, and you won't detect this collision here, but you will detect the collision here. So you do a few extra calculation cycles, more than you'd have to, but you save a lot of memory. And that turns out to be a practical way to find it. So that's a time-memory trade-off. It takes more calculations, but less RAM. All right, and that's what this shows. By the way, this also shows you something else. If you start from a different starting value, you might very well end up in the same loop and have the same value. But you could also end up in a different loop in principle. And so we did this in the projects. Here's a simple 1 byte hash value where you find a collision quickly, and in the projects you had to go up to something like an 8-byte hash value. So let's try some Cahoots. That's 10, 6. All right, I'll give it a few more seconds. All right. All right, so which hash functions have collisions? Right, they all have collisions in principle. By simple mathematics, there must exist collisions in every hash function. All right, how many calculations will it take to find a message that hashes to a specific 32-bit hash, like, say, all zeros? All right, 2 to the 32 is what you'd figure. If you try 2 to the 32 random messages, you'll pretty much cover all the options, and you have a pretty good chance of finding any particular value you want. That is the pre-image attack. All right, how many calculations to find a hash collision for a 32-bit hash? All right, that's much easier, 2 to the 16, because of the birthday attack. You only need to get to the square root of n. So that's what we were doing in the projects we went through last week. All right. All right, what method uses more RAM but less CPU? That's rainbow tables. Rainbow tables pre-calculate something and make a big table in RAM and then look it up. Yeah, Rho does not have either of those properties, all right? But the rainbow tables do. What method uses more CPU but less memory? That's what the Rho does. You have to do extra cycles of CPU, but you don't save as many values. All right. And what method uses more RAM and more CPU? That's blockchain, especially as used in Bitcoin. You waste an incredible amount of memory and CPU, storing huge things and doing calculations on them redundantly in thousands of places. And supposedly you gain the benefit of one entity having control over it. But it's a very expensive benefit, and you pay for it by multiplying the amount of computing work by a huge amount, like 1 million. All right. Woot, I think I know who that is from before. JC, I think you might know who that is from before too. I'm not sure. I'll check. And that's a real name, I think. Good. All right. All right. So let's go back to here. So to build a hash function. The way all the ones we're currently using work, and I think all the ones proposed, they all work. You could say you might have to have the whole message in memory and do some calculation on the whole message, but none of them work that way any more than any of the encryption routines we talked about do. They work on blocks. You break it up into blocks, like 128 bits, and then you do something on each block, compression or permutation. The simplest one is to use a compression function, where you have. This is what almost every hash function that anybody uses works this way. So you start with an initial value, like H0, and then you feed in a block of message and run it through a compression function that combines these to make a block of output, and then you bring in the next block of message and do it again and again and again, and off you go. And these compression functions are typically just an encryption function. So there is an issue of padding. If your message doesn't fill the last block completely, you have to pad it. And here's the padding routine that is typically used. Here's the message you have that say only these bits here. So you put a 1 here, and then fill all the rest with 0, except at the end, you put in the length of the message in binary. So you know that only the first 8 bits of this count. So that's a simple way to pad it. That'll do it. This is what SHA-256 uses. So to build the compression function, you typically just use a block cipher, and the block cipher has a key, but you can just use the message block as keys. That's one way to go. So you have in either a starting value or the hash of the previous block, and you encrypt that using the next message as the key and get the output. And then in order to prevent people from decrypting it, if they know the key, you XOR input to output so it's not reversible anymore. Because remember, you don't actually want the reversibility of an encryption function. You're just using an encryption function just because it's a handy thing sitting around that you know the security properties of. So there are other compression functions we talked about. These are sort of like the complicated. There are other ways to mix the input and output in more complicated ways, which amount to similar things, but they're just not as popular. And so that's one way to do it. Another way to do it is a sponge function. it kind of makes no sense to use an encryption function that has a key and then somehow destroy the reversibility of the key. Why did you have a key anyway in a hash function? And key check for SHA-3 is the sponge function that works without a key. And so what it does is you have an internal state here, and your internal state is much bigger than the blocks. So you feed in an initialization vector, you then feed in some message and permute it, combining it with the key, with the internal state, and then bring in another message and mix it with the state and another message and mix it up with the state. You eventually, the state function, which is big, like 1,000 bits, comes out here, and then you just pick some of those bits to be the hash function. This turns out to be, so they call this the absorbing page. It's like a sponge. You give it some bits, give it some more bits, give it some more bits, it soaks them all up, and then you squeeze some bits out of it. That's where that's the hash value. But there is no key, and this turns out to actually have more desirable mathematical properties than the old-fashioned system where you turn an encryption scheme. Yes, the M's are blocks from the same message. So your message is just broken up into blocks, and off you go. And I think you'll have to pad the last block the same way. Yep. There's a guy who bought a PowerBook, forgot his password, and threw it away without asking anyone for help. Oh dear. Yes, because as you know, login passwords are mostly ornaments, especially a few years ago. Unless you have BitLocker Drive encryption, the login password is just an ornament. Yeah. And there are attacks. Yeah, that's a shame. That used to be like the first or second project when I taught Windows tech support, and even my hacking house was get past Windows passwords. That's a crowd pleasers. Students are very pleased to see how easy it is to get past them. Not anymore, now that you have BitLocker Drive encryption. Now there's not a good way to get past them, but there used to be. So the SHA family. MD5 was one of the earliest hash functions, and it was never approved by NIST for any purpose. In 2005, they were able to make collisions, and now you can do it pretty fast, but it cannot be reversed. It still has strong pre-image resistance, which we talked about in those green slide things. To actually make a message that would calculate to a precise MD5 you want is very difficult, but to create two messages with the same MD5 is not so difficult, as long as you're willing to craft the messages carefully. SHA-0 was the original SHA function approved in 95, but it was replaced by SHA-1 in 93, replaced 2 years later to fix a security issue which, as far as I know, no one has ever figured out. But somebody, probably the NSA, told them not to use it and use SHA-1 instead. This was designed to be the replacement of MD5, and the first one approved by the government. So it was 160 bits long. The idea was that you would have to do 2 to the 80 calculations to make a collision, and at that time they figured 2 to the 80 was a monstrous number that you'd never reach, so that would be enough security. The problem is, there was a shortcut. Mathematically, it would take you down to 2 to the 60, and then they found more and more shortcuts until they got it down to 2 to the 33 for SHA-0, and 2 to the 60 for SHA-0. SHA-1, however, held for a long time, and was only broken a few years ago by Google. So it uses an encryption function called SHA-cal, and it does this hash block. It encrypts the message and the hash and combines that with the old hash. Very much the same construction we talked about. And so what you do is you take 160-bit internal value broken up into 5 32-bit words, and this is, you do this mathematics on them, combining these bits, these blocks together. So in 2005, that's when an attack was found that would shrink this down to 2 to the 63 instead of 2 to the 80. And in 2017, Google managed to do it. They made 2 PDFs that hash to the same SHA-1. That, again, that doesn't mean, for example, if you're doing a forensic investigation and you take a hard drive image and you attach an MD5 hash to the image, that's actually a perfectly fine thing to do. Because the point of that MD5 is so when you make a copy of that image and give it to, say, the other side in a lawsuit, they can calculate the hash, and if it matches, that means nobody modified the image. And even MD5 is good enough for that, because that's pre-image resistance. It's second pre-image. The question is it possible that somebody altered the evidence and still had the same MD5 hash? And that is not possible even now. That would take 2 to the 128 calculations. So, for many purposes, MD5 and SHA-1 remain perfectly fine, but they do have some defects. There is a SHA-1 collision. It's not great to have a SHA-1 collision. You would rather use a function that has no known collisions, where they're so far apart you really can't find them, so they moved up to SHA-2. And SHA-2 is just much longer. Instead of 160 bits, it's 224 or more, so the most common version being SHA-256, and there it seems like you should be fine here. And so the problem is no one has ever found any collisions in SHA-2, and no one expects any to happen soon, but the problem is the mathematical underpinnings are similar to SHA-1. So people are afraid that it may turn out to have weaknesses like SHA-1, and maybe it's not trustworthy. So we had the competition with the National Institute of Standards that ended a couple of years ago. Here's the last 5 finalists. These 5 functions competed to be awarded the prize of SHA-3 after 50 or 60 early candidates, and they chose Chacha to be SHA-3. So we have SHA-3 in case anybody ever cracks SHA-2. So it's got the same sort of sizes available, since it's a sponge function, you can produce hashes of any length. You can take any one of the bits you want out of the end, and so there's algorithms called Shake-128 and Shake-256 to produce these hashes, and these are not the size of the hash, these are the estimate of the security category it's in, how many bits of security it has. So it has a sponge function with a 1600-bit internal state, and it takes blocks of data and scrambles them into there. So, and then your author wrote Blake 2 after the SHA-3 contest, and he says it's better than the winners of SHA-3, but it wasn't out fast enough to be considered. And of course, to be fair, that also means it probably hasn't received the inspection of those SHA candidates, but it is pretty popular. And the point is, the problem with these other ones is they keep getting slower. SHA-1 is real fast to calculate. It's in fact faster than MD5. But SHA-2, which is SHA-256 here, and SHA-3 are much slower to calculate. And a lot of people don't like this. And so Blake is actually faster than SHA-1, faster than any of the others. He designed it to be fast to calculate, which is a consideration for a lot of people. So it uses a sponge function. And so it's got 2 functions, one for 64-bit and one for 8 to 32 bits, and is considered to be the fastest secure hash available. And it's not a NIST standard. It's not approved by the government, but it's used by many apps and libraries like OpenSSL and Sodium. And I mentioned before, Sodium is the new encryption algorithm. We'll use it in the projects. It is the one that uses the very latest form, none of the standard stuff, not RSA or anything, but the new improved versions that have been developed after those were approved, and is in principle more advanced and better. So Blake's, the compression function, you have a block cipher based on Chacha, and so again you feed in messages and encrypt them, and then do some XORs, and then you have the next hash values. This is the compression function. So it's got these 4 64-bit words, and you scramble them together with this stuff, which you maybe, I don't know who named it Sodium. Pretty strange idea, isn't it? But that's the modern encryption library that is in principle better than the old-fashioned stuff, like RSA. Although most people just continue to use the official government-approved stuff, which was approved like a decade or 2 ago, and is therefore somewhat older, but if used with long enough keys, they're all considered pretty good. So you've seen this before in some of the other modern tricks. You just use XORs and right and left shift of bits, and that's really fast. This is why it's fast. You use these very simple transformations. So here's things that can go wrong. If you use the wrong hash function, for example, like if you use CRC32 to sign something, then you're going to get hacked. That's because it's not a cryptographic hash algorithm. It's just not secure enough. And the other thing I mentioned, this is the one that actually matters much more. All the hash algorithms we're currently using are subject to this length extension attack because they use blocks. If you were to know, if you know the hash of a message, you can calculate the hash of a longer message from it. So this is the issue. If I have blocks of data coming in, M1, M2 is the message, and I know this hash, I can create a valid hash by adding more to it without knowing the original message. You just take the current hash value and you can add more to it. That is an undesirable property. Now, if the message was properly padded, then actually, if you know the hash of M1, M2, the M2 here is not really full of message. It has that padding at the end. So if I were to add an M3 to it and calculate that hash, then it wouldn't really be a valid hash of a normal valid message. It would have this padding in the middle of it, which is screwy. But anyway, some applications do get fooled by it. And that's the game. If you achieve SHA-2 is vulnerable, they're all vulnerable. They all have this property, the same property that makes it easy to calculate because you don't need to code much in memory. You build in a block of message, you calculate the hash value, then you just add more to the hash value over and over. It makes it susceptible to length extension attacks. And you could have avoided it if you made the last step different. If you did something different in the compression function for the last step, then doing another compression after that would not be valid anymore. But none of the functions we're using do that. But Blake does, of course, because it's a modern function and aware of these problems. All right, so here's what you might do, for example, if you have a cloud storage thing like Dropbox, where they have stored files, and then you want to make sure they've really stored your file, you could send a challenge up, and the server calculates hash of message challenge as a response, and you calculate hash of message challenge, and if it's right, then you know they have your file. That's the idea. But they could have just stored the hash value and not stored your whole file, and they'd still be able to calculate this and spoof the response. So the server could lie to you and claim to have your file, and this test would not prove that they had your file. So that's a weakness, and of course you could have cured that by using the challenge before the message. And then the server can only calculate this if they know the whole message. So, I mean, it's really, and anyway, that's the sort of thing which is a flaw in the protocol. This part where you keep adding more blocks of messages to the previous total does have some weaknesses. And that's the techniques that's used to make MD5 collisions in the software I've seen, and I'm pretty sure it's the technique that Google used to make that SHA-1 collision. All right. And that's why a lot of people get upset. They say, the fact that there's a collision in MD5 and SHA-1 does not really mean that they're useless for most purposes. It just means they are not 100% perfect. The particular defect they have is probably not going to matter in most cases. But anyway, you might as well use something that has no flaws at all, like SHA-2 or SHA-3. And you could say the same thing about sodium. I mean, most people just continue to use the old standard approved algorithms because they really are still okay. But the new ones are supposedly better in a theoretical sense. But there's no particular reason to jump on them. And there's a reason to avoid them if you want your software to be used by the military and governments. I think Sodium is just an open source project written by, cryptographers and open source developers. It hasn't been through any government approval, I think. All right. All right. Which one uses a sponge function? Yep, SHA-3. All right. Which one uses a Merkle dam guard construction? They all do. They all work that way except SHA-3. And by the way, I'm pretty sure this is the same Merkle that made the Merkle tree that made the blockchain. All right. All right, which one uses key check? Which I am probably pronouncing wrong. That's SHA-3. Good. And which hash collision was found in 2017? That was SHA-1. All right, which one of these is the fastest? Blake, the newest and fastest, but not a government approved. All right. All right, there's Twisted. And Woot. All right, good. I've got the winners. All right, so I'm going to stop recording this.